Good morning, everyone. Today, I'm excited to present DM1, MeanFlow with dispersive regularization for one-step robotic manipulation. In this work, we address a fundamental challenge in robotic manipulation: how to achieve both fast inference and high performance simultaneously. Current diffusion-based policies require 50 to 100 inference steps, making real-time deployment challenging. We'll show you how DM1 achieves 20 to 40 times faster inference while actually improving success rates by 10 to 20%. Let me start by illustrating the core problem we're solving. On the left, you can see a critical issue called representation collapse. Look at these two similar observations of robotic scenes. Without our method, these visually distinct situations produce nearly identical internal representations, leading to incorrect grasps. With dispersive regularization, shown in the right panel, the features are properly separated in the latent space, enabling correct decision-making. This landscape diagram illustrates the traditional speed-quality trade-off in robotic manipulation. Existing methods force you to choose either fast but inaccurate or accurate but slow. But here's our key result. DM1 breaks this trade-off entirely. We achieve both superior success rates and dramatically faster inference times, up to 40 times faster than baseline methods while maintaining or exceeding their accuracy. Now let me explain how DM1 achieves this breakthrough. Our framework has 4 key components. First, the one-step action generation mechanism. Unlike traditional diffusion policies that require many denoising steps, MeanFlow learns average velocity fields that enable direct transformation from noise to actions in just one step. This is the foundation of our efficiency. Second, we use a vision transformer encoder to process RGB observations. This extracts global visual features through patch-based tokenization with positional encoding, providing rich representations for manipulation. Third, and this is our key innovation, we apply dispersive regularization to multiple embedding layers. You can see 3 types: temporal dispersion, noise dispersion, and conditional dispersion. These components actively prevent representation collapse by encouraging embeddings to spread out in the feature space. Finally, here's the complete computational flow. Visual inputs, proprioceptive states, and temporal conditions flow through embedding modules. Dispersive losses are applied at intermediate layers to maintain feature diversity, while the MeanFlow loss ensures accurate velocity field prediction. This architecture elegantly combines efficiency with robust representations. The key insight is that by regularizing intermediate representations across multiple modalities, we prevent collapse without sacrificing the one-step generation capability. Let's look at our comprehensive evaluation across 4 robotic manipulation tasks: lift, can, square, and transport. Each row shows a different task, and each column shows different dispersive weight configurations: 0.1, 0.5, and 0.9. The critical insight is on the horizontal axis. We evaluate from 1 step all the way to 128 steps. Notice our MeanFlow-based approaches, the solid lines with circles, achieve excellent performance with just 5 denoising steps. In contrast, the baseline methods shown in dashed lines require 32 to 128 steps to reach comparable success rates. Look at the can task in the middle row. Our MF plus DISP method achieves 80% success rate at just 5 steps, while shortcut needs 32 steps and reflow needs 128 steps to reach similar performance. That's a 6 to 25 times reduction in computational cost. The advantage is even more pronounced on complex tasks like transport in the bottom row, where baseline methods struggle even with many steps, while our method maintains robust performance. This demonstrates that dispersive regularization is not just maintaining performance, it's actually improving it while dramatically reducing computational requirements. This slide directly visualizes the speed-accuracy trade-off I mentioned earlier. The y-axis shows success rate, higher is better. The x-axis shows inference frequency, left means faster. So the ideal region is the upper left corner, high success and high speed. Our MF plus DISP methods consistently occupy this optimal region across all 4 tasks and all weight configurations. In contrast, shortcut and reflow are pushed to the right, they're much slower, and in many cases they also have lower success rates, putting them in the worst possible quadrant. Quantitatively, we achieve 0.07 to 0.09 seconds per inference, compared to 0.6 to 0.8 seconds for shortcut and 2 to 3.5 seconds for reflow. That's our 20 to 40 times speed up while maintaining 10 to 20% higher success rates. Now let's look at the detailed quantitative results in Tables 1 and 2. Table 1 shows reward comparisons under both 1-step and 5-step denoising across different dispersive weights. We compare against reflow, shortcut, and several dispersive variants. Look at the task with weight 0.5. At 1 step, MF plus DISP achieves a reward of 100.3, compared to 76.2 for reflow and 84.5 for shortcut. Even at 5 steps, we maintain this advantage. This pattern holds across most configurations. Interestingly, the optimal weight varies by task complexity. For simpler tasks like lift, higher weights work well. For complex tasks like transport, lower weights around 0.1 provide better balance. Table 2 compares performance under optimal configurations for each method. Here's the key result. MF plus DISP with just 5 steps outperforms shortcut with 32 steps and reflow with 128 steps. For lift task, 97% success rate versus 84% for shortcut and 78.5% for reflow. For transport, the most challenging task, 53% success versus 34% and 39%. That's a 55% relative improvement on a complex manipulation task. This table also shows we achieve 6.4 times speedup over shortcut and 25.6 times over reflow while maintaining superior performance. Now let's move from simulation to real-world deployment and see how DM1 performs on a physical Franka Panda robot. First, we show the detailed latency breakdown for the lift and tasks. 4 motion planners were tested: Cartesian, BiTRRT**, RRT Connect**, and RRT star. Each row decomposes the control pipeline into camera capture, state reading, pre-processing, inference, motion planning, and command sending. The key metric is inference time. With MF1, DM1 achieves only 2.4 to 2.5 milliseconds. Even with MF5, it stays around 10 to 13 milliseconds, still extremely fast. In contrast, shortcut 32 takes about 76 to 79 milliseconds, and reflow 128 exceeds 300 milliseconds, making DM1 roughly 730 times faster. The best configuration, MF5, with Cartesian planning, achieves 19.2 milliseconds total latency, enabling real-time 50 Hz control for reactive manipulation. Figure 5, left. Lift. The left panel shows the lift task with a red cube. The top strip are wrist-mounted first-person snapshots. The bottom row has 2 third-person videos. Left/green, our method succeeds. Right/red, the baseline fails. Figure 5, right. The right panel shows the task with a Coca-Cola can. Same layout. Top is the wrist view. The bottom row shows 2 third-person videos. Left/green, our success. Right/red, baseline failure, affected by reflections and cylindrical geometry. The leftmost sidebar lists the hardware/object context. Franka Panda, RealSense D435i, task/object names. Let me summarize the 4 main contributions of this work. First, we break the fundamental speed-accuracy trade-off that has limited robotic manipulation policies. DM1 achieves 20 to 40 times faster inference while simultaneously improving success rates by 10 to 20%. This isn't just an incremental improvement. It's a paradigm shift showing these goals aren't mutually exclusive. Second, we provide the first systematic solution to representation collapse in 1-step generation for robotics. By applying dispersive regularization to intermediate embedding layers, we maintain discriminative representations without architectural modifications or complex training procedures. Third, we conduct comprehensive evaluation of 4 dispersive regularization variants across multiple tasks and weight configurations. Our analysis provides practical guidance. InfoNCE-based and covariance-based methods work well, and weight selection should consider task complexity. Fourth, we validate DM1 on a physical Franka Panda robot, achieving 19.2 milliseconds latency that enables 50 Hz plus control. This demonstrates the practical viability of one-step generation for real-world robotic systems. Thank you.